All right, these are the matter and classification section of the notes. So in your note packet, the first things we talk about is just what is matter, okay? Well, matter is anything that has mass and takes up space. That needs to be written in your notes. Matter is anything that has mass and takes up space. So you need to make sure you go ahead and highlight that, or actually you need to write that in your notes. Matter is different than mass. Mass and matter are not the same thing. Notice in the definition of matter, the word mass appears. So what is mass? Mass is the amount of matter an object contains. It can be measured in different things, like most of the time it'll be measured in grams or kilograms. It could be measured in pounds. Okay, all of those would be mass measurements. It can also be measured in moles or number of molecules. But matter is the anything that has mass, so it has a specific amount of matter, or it's a specific amount of stuff, and then how much space it takes up, which that's actually volume, by the way. All right. So the law of conservation of matter. So hopefully you did get those two statements written into your notes. Matter is anything that has mass and takes up space. Mass is the amount of matter an object contains. Okay. If you need to pause this to get these written into your notes, then please ask for that to happen. Now, the law of conservation of matter, which also needs to be written in your notes, let's break it down, okay? So let's define the individual pieces of this first. Okay, a law is summarizing statements of many experiments. Conservation is to stay the same or saved. And matter is anything that has mass and takes up space. So the law of conservation of matter is matter cannot be created or destroyed. It is saved before and after a chemical reaction. So it can be rearranged or changed, but it can't be created or destroyed. So you need to make sure that you write the altogether part of it. Matter isn't created or destroyed, but it is saved before and after a chemical reaction, or it's rearranged, but it ultimately is the same amount. Okay. So again, make sure you get that written into your notes. It cannot be created or destroyed, but it can be rearranged in a chemical reaction. But it's always the same amount before and after. Now, the kinetic theory, which isn't actually written in your notes per se, but the kinetic theory is discussing the motion of particles. Okay, kinetic means motion. All right, and remember, so it states that all tiny particles of matter are in constant motion. Every single one of our cells and our atoms are vibrating all the time. We don't feel them individually, but they do vibrate. Okay, so the kinetic theory and kinetic energy, kinetic energy is the energy matter has due to the motion of its particles. And so really when we measure kinetic energy, we measure a temperature, believe it or not. But the kinetic theory really helps us to distinguish the different states of matter. Okay, so even the particles in your desk right now are moving. All the particles on the floor are moving. All the particles in the air are moving. Everything is moving. Okay. Now, because of that, we have states of matter. Now, solids have a definite shape and volume. And you're going to want to add that to your notes in the solid section. The particles in a solid are move slightly just back and forth. They don't have enough energy to move around or out of place, so they just kind of vibrate. It would be like if I squished everybody in the classroom into one corner and said everybody has to stand with their shoulders touching and all you can do is rock back and forth on your feet. That would be like a solid. Okay, that would be representative of a solid and the atoms of solid. Then we have a liquid, and a liquid, oh, and actually I want you to draw this picture. Go back for a minute to the solid. Draw that picture of those particles in your square. Okay, so draw a picture of a solid. That's logistically what you're drawing, is all those little particles all right next to each other. So take a little bit of time and make sure you get the definition. Definite shape and definite volume. They only move slightly back and forth, and then draw the picture. Again, this could be when, if you need us to pause the video, we can pause it at this time. All right, so with our liquid, a liquid has a definite volume, but no definite shape. Okay, you could measure its volume, for example, in a graduated cylinder, or when you get a water bottle, it tells you what the volume of the liquid inside of it is. It's 16.9 ounces. So the particles in a liquid have enough energy to move out of place, and what they do is they slide past one another. So they have the energy to move and slide past one another. So again, make sure that you write that a liquid has a definite volume, but no definite shape. The molecules can slide around one another, and then draw the picture. All right, and then our final state of matter that we're going to talk about is gas. And a gas has no definite shape or volumes. Make sure you get that written. The particles have enough energy to completely separate from each other, so they just bounce off of each other all the time, sort of like go-karts or bumper cars. They'll just bounce off of the sides of the container or off each other, but they don't really stay together, and that's what makes up a gas. Okay, so again, make sure that you get it written into your notes. It's no definite shape or volume and enough energy to separate from each other, and then draw the picture. All right, so um, a piece of ice melts to room temperature water. Are the particles that composed the ice the same now that it has melted? Okay, so when you think about it, are you still talking about water? Okay, water is two hydrogens and one oxygen. When it's in its ice format, it's still two waters and or two hydrogens and one oxygen, but as they change kinetic energy, are the particles that's composing the ice the same now that it's melted to the room temperature of the water? Take a little bit of time and discuss that with your neighbor if you think they are yes or they're no, not no. Figure out your answer yes or no. This is when you can pause and you guys can discuss things, see if you can come to a consensus about whether you think the answer to this is yes or no. There is actually an answer. And so, yeah. So hopefully everybody did come to the consensus that They are the same particles. They're composed of the exact same particles of just H2O molecules, but they've just got a different amount of energy now. So that's the only difference in it. Okay, so for this quick check, you have these questions in your notes, and I want to give you maybe about 30 seconds or so to figure out the answer to each one of these. Which state of matter has particles with the highest kinetic energy, which state of matter has the lowest kinetic energy, and which state of matter has the lowest density. So hopefully everybody has answered the questions. Now turn to your table mates and discuss your answers and see if you guys have the same thing, and talk specifically about that last one, which state of matter has the lowest density, and explain your reasoning for your answer with your neighbors. Hopefully you did say your answers were which state of matter has particles with the highest kinetic energy, which would be a gas, which state of matter has the lowest kinetic energy, which would be a solid, and which state of matter has the lowest density. Density is how tightly packed the molecules are together. So the lowest density would also be a gas. Okay? We'll talk about density a little more in the next units, but that's kind of that preview. All right, so let's talk about the classification of matter now. In your notes, we have matter can be a substance, and a substance is matter that has a definite and uniform composition. So make sure you fill that word in with your notes and maybe highlight or underline some things. A mixture is a physical blend of two or more substances. They can be physically separated. How can things be physically separated? You guys can kind of think about that of we can literally pull things apart by using a magnet. We could use a filter. There's lots of different ways that we can just take things apart. Um, yeah. So to answer the question about how, think of salad with tomatoes, lettuce, carrots, cheese, and onions. How would you know two objects you picked up were different? Okay, so that's kind of a way to think about how you can separate a mixture physically. Okay. So heterogeneous mixtures. So mixtures can be broken down further into two different categories. And the heterogeneous mixtures are not uniform in composition. They consist of two or more phases lots of times. So meaning like salads, we have all kinds of different, but they're not the same composition. Like there's not exactly the same number of tomatoes as there is lettuce, as there is, croutons, as there is whatever, even salad dressing. So, I mean, they just have a different value there. Chocolate chip cookies, every single bite doesn't have exactly the same number of chocolate chips in it, things like that. Okay, so that would be a heterogeneous mixture. Make sure that you get that definition written in your notes, and you might even want to write down a couple of those examples. Now, a homogeneous mixture is one that is completely uniform in composition. So it looks the same throughout. it's typically called a solution. Some is one of them, and it is all in one phase, meaning you can't really tell the difference. Milk is when you look at your milk, you buy homogenized milk, and that's because the milk fats and the water and just the liquid milk is all mixed together, and you can't tell the differences between them. And so that's why it looks the same throughout. Salt water, everything looks the same. Coffee, tea, your blood. You can't tell the difference that there's white blood cells, red blood cells, plasma, all those things in your blood, but all those things are there. So again, you might want to make sure you write this down in your notes. It's a uniform composition, looks the same throughout, and then write down some of the examples. If this is where we need to take a pause real quickly for you to get all that into your notes, then let whoever know and they can pause. Now, substances can also be broken down into two different categories. So mixtures could be broken down into two types, but substances can as well. And those two types would be elements and compounds. So elements are the simplest form of matter that can exist under normal lab conditions. And these are all on the periodic table. They have their own individual square. And so if it's an individual square on the periodic table, it is an element. Okay, aluminum, carbon, mercury, all of those have a square on the periodic table, so they are elements. Okay, the other one would be compounds. Now, compounds are substances that can be separated into similar substances, but they can only be separated by chemical means. They are made up of two or more different elements. That's going to be the key of a compound. Okay, if you think about a compound word, it's two words put together. So compounds are actually just two or more elements put together as well, but they're chemically bonded. So we have like aluminum chloride, we have salt, which is sodium chloride, we have carbonated water. We also have, I don't remember what this picture is. Sorry, I'm going to move this. Methanol. Methanol is carbon and hydrogen and a hydroxide. So it's a lot of different things put together. So that's always key to kind of think about. Okay, so those are all compounds. So make sure you got those two definitions and that you filled in the two blanks with elements and compounds. Elements are the simplest form and on the periodic table. Compounds are two or more different elements, and they can only be separated by chemical means. Okay? So this part is not in your notes, but you do need to write it in your notes. So if you can find a blank spot to write this anywhere, you're going to want to write it. Alloys versus allotropes. And these are vocabulary words that are on your test. So that's why I'm saying make sure you write them in your notes somewhere. Now, an allotrope is two or more different forms of the same element. So for example, carbon can be diamonds or it can be coal. They're both made of pure carbon, but they're known as allotropes because it's the same element, but it's two or more different forms of that element. Graphite also is carbon, so all three of those are allotropes. Now, alloys, though, are a solution of two or more metals. So lots of the jewelry that we wear is made up this way to reduce the cost, like you have sterling silver, or you have plated silver. So you have lots of, or it's only gold plated. So it's a solution of two or more. Bronze is actually an alloy as well. So bronze and like sterling silver, those would be really good examples of them. So let's do a quick check, and this did not come over to this PowerPoint really nicely for me. So identify the following as an element, compound, or a mixture. I'm going to give you about 30 seconds or so to kind of go through and figure out whether you want to do these as an E, a C, or a mixture. And remember, you do have your periodic tables that you can use. Now, table sugar actually is C6H12O6, and so it's actually three different elements together. So it would be a compound, whereas O2 is just oxygen. So that's oxygen gas, and oxygen has its own square on the periodic table, so that would make it it's actually an element. It's a diatomic element, so I don't know why it has a C there because I don't like that as the answer. So I'm going to fix that because that should not be a C. That should be an E. And then water, maybe that's because those things came up that way. That might be why. Yeah, water's the compound, so those got mixed up because of that. Water is compound because water is H2O. And then you have calcium carbonate, which is CaCO3, which is three different elements put together, so that makes it a compound. Yeah, so we're getting off these, so that's compound, so I'm not going to do all those. Iron has its own square on the periodic table, which would make it an element. Air is actually a mixture of nitrogen and oxygen and lots of different things like that. So it, like I just said, it's a mixture. You can separate those things actually though. Vegetable soup is a mixture as well because you can separate it. Then rust, which is iron oxide, okay, iron Roman numeral 2 oxide, or it is going to be a compound because it's multiples. And then salt water is actually a solution. And since solutions are really homogeneous mixtures, that would make this one a mixture as well. Okay, so I would tell you that those are those. And so it's not going to click in right because the formatting got messed up here. So, all right. And so let's go to our next slide. Now, you do need to take a little bit of time and fill in this flow chart. This would be where I would go ahead and make sure that we go ahead and pause this video and allow you to go ahead and fill in the flow chart accordingly. So you start with matter in the top square, then you're going to have a substance, and then you're going to have mixture in those middle two squares, and then on the substance side under it you're going to have a compound and an element, and then underneath the mixtures you're going to have homogeneous and heterogeneous. Underneath the mixtures and the substances, you can break a mixture down physically into its substances. So that's important to realize. So like we could have broken salt water down into salt and water. So those are two different compounds then. Remembering that compounds can also be chemically separated and made into their elements. So make sure you add those additional arrows. And again, go ahead and pause this so that you can get all this written in your notes. Now there are 6 different, actually phase changes of matter. Would be when they're changing states of matter. That's a phase change. And these, we're going to go ahead and finish this up, although this is kind of going to roam into our next set of notes. So you could stop there if need be. But a phase change occurs when matter is transformed from one state to another. It's important to note that the substance itself doesn't change. It's only the state of matter. So that will be important when we start talking about physical versus chemical changes. Okay, but because the substance itself is not changing, it is a physical change. So I might write that somewhere near the phase change is that it's just a physical change, and when it changes from one state of matter to another. Okay. Then we have melting, and this is melting is a solid to a liquid. That's all you really need to write next to melting is solid to liquid. Freezing is from liquid to solid, so liquid to solid. That's all you need to write. Melting and freezing go hand in hand depending on whether you're adding heat energy or taking it away. Vaporization is from liquid to gas, so liquid to gas. Condensation is gas to liquid. Those two, again, go hand in hand with each other, so it just depends on whether you're adding or taking away heat energy. Then we have, oh, that did not work right. Then we have sublimation. I will tell you that that's over melting, so sorry about that. But it's when it changes directly from a solid to a gas. So directly from solid to gas. And this is an example of dry ice. Dry ice does this. So if you're getting to see some of the dry ice demos, you're getting to see sublimation. Then deposition would be where we go straight from gas to solid. So this is where, again, it skips the liquid phase. These go hand in hand with each other again. Um, if you're always skipping the liquid phase, depending on whether you're taking away energy or adding energy. Okay, and we'll stop these notes here. Have a good one.